Hello and welcome to another session in physics. Well, in this session we'll be looking at the topic electromagnetic field. But before that, let us review the previous lesson. Welcome back. We've defined an electromagnetic field as a field that tends to unify the interactions between an electric field and a magnetic field, as the name implies. In our past couple of lessons, we've been able to explain and put across the point on the behavior or what electromagnetism is all about, and that is the behavior of an electromagnetic field. So at this point in today's class, we are interested in trying to consolidate on that fact and try to explain further the forces acting on conductors that carry currents in a magnetic field. Remember, we said electricity and magnetism comes together to form electromagnetism, and the interactions between their field is what we call electromagnetic field. The interactions between them and the field that they create. From the slide here, you would see that a conductor carrying an electric current, when placed in a magnetic field, experiences a mechanical force. It experiences a mechanical force. Apart from the fact that it experiences electric force, magnetic force, it also experiences a mechanical force. This can be illustrated or demonstrated using two metal rails fixed on each side of a powerful horseshoe magnet. A copper rod is then placed across the rays. When the current is passed through this copper rod, it is observed that the copper rod rolls along the rays toward the right hand side. Then we have to adjust the rheostat. The rheostat is an electronic device that can be used to vary or adjust the flow of electric current. So when you adjust the rheostat, you can adjust the flow of the current flowing through the rod, and by doing that, in this instance, more current is made to pass through the rod. One will also notice that the rod moves faster, and thus the force on the rod increases when the current increases. On the other hand, if the direction of flow of current is reversed, by reversing the connections at the battery terminals, the rod will be observed to move towards the left, opposite to the previous direction of motion. At this point, let's talk about Fleming's left-hand rule. Fleming was intrigued by the interactions between electromagnetic field, between an electric field and a magnetic field, or conductors and magnets. So he had to propagate a theory that shows us the direction of the force on a current in relation to the magnetic field. So this principle or this interaction is given and explained using Fleming's left-hand rule, which states that if the thumb, forefinger and middle finger are held mutually at right angles to one another, with the forefinger is your index finger, the one you see here on the screen, with the forefinger pointing in the direction of the magnetic field and the second finger pointing in the direction of the current, then the thumb will point in the direction of motion, or the force producing the motion, the force acting on the conductor. So analyze it critically here from the diagram and you would understand. You see the thumb is showing the direction of the electric force, the forefinger, the index finger is showing the direction of the magnetic field, and the middle finger is showing the direction of the current. Now let's look at applications of electromagnetic field. In electric motors, the applications or the importance of an electromagnetic field cannot be overemphasized. When we were talking about different kinds of dynamo or generators, we said that an electric motor is a device that converts electrical energy into mechanical energy. It is a kind of dynamo, and it consists of the following: a rectangular coil of insulated wire, which we call an armature, The second, it is comprised of a powerful magnetic field in which the armature turns and is provided support by two curved poles of powerful magnets, two curved core pieces of powerful magnets. And the third part of an electric motor is a commutator. A commutator is a single split ring which has been segmented into two halves, each of them insulated from each other. If you remember vividly, we said that a commutator can be used to replace two split rings so that we can be able to use that AC generator and produce DC. So using AC to produce DC can be done by removing these two split rings and replacing it with a commutator. A commutator is a single split ring, one split ring that has been segmented into two halves and they have been insulated from each other. And now the fourth part of an electric motor is two carbon brushes that are made to press slightly against either side of the split ring commutator. Now let's talk about a moving coil galvanometer. A moving coil galvanometer is one of the most sensitive and accurate instruments we use for detecting or measuring extremely small currents or potential differences, and it is used extensively in the study of electromagnetism or in detecting charges or currents in electromagnetic fields. It consists of essentially one, a light rectangular vertical coil that has been pivoted in jeweled bearings so that it can move in a vertical plane. It also consists of two curved pole pieces of a horseshoe magnet and a soft iron core or cylinder inserted between the pole pieces. And then thirdly, it consists of two spiral non-magnetic control springs of phosphorus bronze, each of which is attached to the jeweled bearing or spindle. You see here that current enters or leaves the rectangular coil through these spiral springs. The springs also provide what we call the control couple. At this point, let us talk about the force on a moving charge in a magnetic field. The force on a charge Q moving with a velocity V in a magnetic field of strength B is given by F equal to QVB. I'll tell you what F equal to QVB means. F is the force on the charge, and we know already at this point that force is measured in newtons. Q is the charge on the body, and then we have V. V is the velocity of the body, and then we have B. B is the magnetic field, the strength of the magnetic field. And magnetic field, of course, I forgot to add that charge is measured in coulombs. Velocity, of course, is measured in meters per second. And magnetic field is measured in Tesla. Tesla, T. That is the unit of measuring the strength of a magnetic field. Do go through the notes that has been attached at the end of this video for more information. Thank you so very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.